Hello everyone. Today we are going to do the chapter Electromagnetic Spectrum of Organic Chemistry of B.Sc Part 3. Analytical chemistry deals with the study of detection and estimation of organic and inorganic elements and compounds. Before 1920, the composition are known by volumetric and gravimetric analysis, which are called classical methods. In this method, the analysis of compounds was tedious and time-taking. Beaker, burette, pipette, glass tube, conical flasks, etc. are used in classical methods. After the discovery of spectroscopic technique, the analyses are carried by modern instruments like UV, IR, NMR, mass spectrometer, etc. The main advantages of instrumental method of analysis are the process is very fast, small sample can be used, that is approximately 10 to the power minus 7 to 10 to the power 9% only. Complex compounds can be analyzed, and it is a highly sensitive and more reliable and more accurate method. Now let us talk about radiation. It is the form of energy which is transmitted in any medium, or in other ways we can say when emission or absorption of energy takes place in the form of ray, it is called radiation. Now what are electromagnetic radiations? The different form of energy having dual character, that is wave as well as particle character, and consist of electric and magnetic field which are perpendicular to each other are called electromagnetic radiations. The important characteristics of electromagnetic radiations are, as we know, E is equal to h nu, or we can say energy which is equal to hc by lambda. Energy of these radiations are directly proportional to the frequency and inversely proportional to their wavelength. Also, the electromagnetic radiations travel in space and do not require any medium. And all the electromagnetic radiations travel in space with same velocity, that is 3 into 10 raised to the power 8 meter per second, that is the velocity of light. All electromagnetic radiations are described in terms of lambda, nu bar, that is wave number, etc. Now let us recall the terms which we are going to use in this chapter. The first term is wavelength. The distance between two adjacent crests or troughs is called wavelength. We know 1 nanometer is equal to 10 raised to the power minus 9 meter, which is also equal to 10 raised to the power minus 7 centimeter. And it is equal to 10 raised to the power minus 3 micrometer and 10 angstrom. Second is frequency. The number of waves which pass across a point in 1 second is called frequency, and it is measured in hertz or cycles per second. The third is wave number. It is the reciprocal of wavelength and the number of waves per centimeter. Electromagnetic spectrum. The arrangement of all types of electromagnetic radiations in increasing order of their wavelength or decreasing order of frequencies is known as electromagnetic spectrum. The order is cosmic rays, gamma rays, X-rays, UV rays, visible rays, IR, micro, and radio waves. When we go from left to right, the wavelength is increasing, and when we move from right to left, the frequency is increasing. And we have a trick to remember these radiations. Classical Gaudy XUV in my range. Classical is cosmic, Gaudy is gamma, X is X-rays, UV, U, V visible, in is for IR, mi for micro, range for radio. Next is spectroscopy. It is the interaction between electromagnetic radiation with the compound under investigation. Next, we have the principle of absorption spectroscopy. When molecule exposed to electromagnetic radiation, it may absorb energy, due to which its energy increases. The absorption energy depends upon the molecular structure. The increase in energy level is due to increase in vibrational or rotational energy of the molecule. The record of the amount of radiation absorbed by a given sample as a function of electromagnetic radiation is called absorption spectrum. The spectrum is made of absorption bands with peak of maximum intensity, and the instrument which is used for this is called spectrophotometer or spectrometer. Absorption of energy leads to excitation of molecule from lower energy level to higher energy level. So now, the first kind of spectroscopy we are going to study is ultraviolet or UV spectroscopy. The study of interaction between electromagnetic radiation in UV region and the visible region by a substance under investigation is called UV spectroscopy. Now look at this table. From 150 nanometer to 200 nanometer, we have vacuum UV region. From 200 to 400, it is UV region. And from 400 to 800, it is visible region. UV spectroscopy is also known as electronic spectroscopy because the absorption of light involves the transition from one electronic level to another level within the molecule. That is from sigma pi n to sigma star and pi star. Don't worry, we are going to read all this in detail in further video. So what is the principle of UV spectroscopy? When electromagnetic radiation in the range of 200 to 800 nanometer is passed through a molecule, the change in electronic state from lower to higher energy level takes place, and it is associated with electronic state. Each electronic level is further associated with a number of vibrational sublevels with small energy separation, and each vibrational state further has a series of number of rotational sublevels with still smaller energy separation, which are also quantized. That is, first we have an electronic level, which is further splitted into vibrational levels, and the vibrational levels are further splitted up into rotational levels. So, an electron can go from any of the sublevels in the ground state to any of the sublevels in the excited state. As a result, UV visible spectra of organic molecules consist of broad bands rather than sharp peaks. Now we are going to study about the absorption laws. You must have studied these in previous classes also. There are two laws which relate the absorption of light by a substance with its molar concentration and the length of path through which the light passes. These two laws are Beer's law and Lambert's law. Beer's law. When a beam of monochromatic light is passed through a substance dispersed in a non-absorbing solvent, the absorption of light is directly proportional to the molar concentration of the absorbing substance. That is, log base 10 I naught upon I is directly proportional to C. And this is Beer's law. The Lambert's law states that when a beam of monochromatic light is passed through a substance, the absorption of light is directly proportional to path length of the sample. That is, log base 10 I naught upon I is directly proportional to L. So we can say Beer's law is the relation with concentration C and Lambert's law is the relation with path length L. The combination of these two laws is Beer-Lambert law. Both the laws can be combined to get a general absorption law called Beer-Lambert law. According to Beer-Lambert law, when a beam of monochromatic light is passed through a dilute solution of substance in a non-absorbing solvent, the absorption of light is proportional to the concentration and path length of the solution through which it is passed. So mathematically, this is Beer's law, this is Lambert's law, and the combination log I naught upon I is directly proportional to Cl is Beer-Lambert's law. And this constant of proportionality epsilon is used here. I naught is the intensity of incident light and I is the intensity of transmitted light. C is concentration of absorbing substance. L is the path length or thickness of the sample, and epsilon is the proportionality constant known as molar absorptivity or molar extinction coefficient. And this term log I naught upon I as a whole is called optical density or absorbance and can be written as A also. So the formula can be written as A is equal to epsilon Cl. This law is applicable for single species and not applicable if solute and solvent interact with each other. So this is a limitation of Beer-Lambert's law. Molar absorptivity epsilon is the measure of intensity of absorption and relates the molar absorption A at a particular wavelength to the molar concentration of the substance and path length of the light. That is, if we keep epsilon here and move C and L to the left side, we get epsilon is equal to A upon CL. And this is the relation between all the terms. Transmittance T, the percentage transmittance, is equal to I upon I naught into 100. Just note that here we are taking I naught upon I, and here we are taking the reciprocal I upon I naught into 100 for percentage transmittance. Now let us see the instrumentation of a UV spectrometer. The modern spectrometer consists of radiation, source, monochromator, cell, detector and recorder. So this is a diagram, simple diagram of the instrumentation. First we have source of radiation, then we have a monochromator. This is a reference cell and this is a sample cell. This is a detector and this is a recorder. The source of radiation. Hydrogen discharge lamp is used as UV region source. And tungsten filament is used for visible region, that is 400 to 800 nanometer. Monochromator, it separates the radiations into single wavelength and split into two beams. Mono means single, chromator means light, so it splits the radiation into two beams at the end. Cells, two suitable transparent containers which do not absorb the light are taken. Quartz cell of 1 centimeter path length is used, and glass cell can never be used. This must be kept in mind. Solvent. The solvent which does not absorb light in the region under examination is taken. The commonly used solvents are 95% ethanol, hexane, and water. Then comes the detector. It measures the intensity ratio of the beams transmitted through the sample and the solvent respectively. The recorder, the chart paper automatically records the absorption of light. Each wavelength in form of graph A is lambda. That is, the recorder depicts a graph between absorption and lambda, or sometimes between epsilon, that is molar absorptivity constant, and lambda. The next topic is electronic energy levels, that is the theory of electronic transition. When electromagnetic radiation in UV region absorbed, there is an electronic transition among various energy levels within the molecule. The transition occurs between a bonding or lone pair orbital and an unoccupied non-bonding or anti-bonding orbital. The energy differences between various energy levels is in most compounds varies from 30 to 50 kilocalorie per mole. Every covalent bond consists of a bonding molecular orbital of lower energy and anti-bonding molecular orbital with higher energy. There are different types of electrons and orbitals present in the molecule. For example, in this molecule, these bonds are sigma bonds. This is also a sigma bond, and the double bond between C and O is a pi bond. These valence electrons on oxygen are called non-bonding electrons and are represented by N. These are sigma star and pi star anti-bonding molecular orbitals. The different types of orbitals with energies are given below: sigma, pi, N, pi star, sigma star. You must have noticed that we have sigma and sigma star as a pair, pi and pi star, but we don't have any N star. This is called non-bonding orbital. Since the N electrons are not in bond formation, there are no anti-bonding orbitals associated with them. In UV and visible region, there are four kinds of electronic transitions which are taking place. That is from sigma to sigma star, from N to sigma star, from pi to pi star, from N to pi star. These are higher energy levels and these are lower energy levels. And the difference between the energies of these levels is called energy difference delta E. Now let us study these transitions in detail. The first one is sigma to sigma star transition. These type of transitions involve the excitation of sigma molecular orbitals to sigma star anti-molecular orbitals. These are called bonding molecular orbitals, these two, and these two are called anti-bonding molecular orbitals, and this one N is called non-bonding. Okay, so these electrons of both the atoms combine to form a sigma bond, but when the excitation takes place, it forms this kind of state and it is called anti-bonding. These kind of transitions are shown by the compounds in which all electrons are used in bond formation. Since sigma bond is very strong, the energy required to cause sigma to sigma star is very high. And separation between sigma and sigma star is also very high. You can see that sigma and sigma star separation is the highest. Such compounds do not absorb in normal UV region because it requires wavelengths less than 200 nanometer. And we have already studied that wavelength of less than 200 nanometer does not comes in the normal UV region. It is in vacuum UV region. Some of the examples are methane, propane, cyclopropane. So the region below 200 nanometer is called vacuum UV region. The normal spectroscopic technique can't be used below 200 nanometer because oxygen present in the air absorbs strong. To study such high energy transition, the entire path length should be evacuated and the region below 200 nanometer is called vacuum UV region. The second transition is N to sigma star transition. These type of transitions involve the excitation of non-bonding, that is n orbitals, to anti-bonding sigma star molecular orbitals. These transitions are shown by saturated compounds containing heteroatoms, such as oxygen, nitrogen, sulfur, and halogens, possessing non-bonding electrons in addition to sigma electrons. So here, saturated means single bond, and heteroatom means all these compounds that have lone pair of electrons on them. You can see oxygen, nitrogen, sulfur, halogen all have lone pair of electrons. So this is a sigma bond, and here we have lone pairs also. These are non-bonding elements. So the transition between this from ground state to lower state causes N to sigma star transition. By increasing the size of heteroatom or decreasing the electronegativity of heteroatom, more wavelength is needed. That is, less energy is needed. For example, the size of iodine is greater than chlorine. Because of increase in size, the wavelength also increases and energy decreases. Similarly, if we compare oxygen and nitrogen, the electronegativity of oxygen is more than nitrogen, therefore wavelength decreases. Due to high electronegativity of heteroatom, more tightly the non-bonding electrons are held. The heteroatom holds more tightly, and more energy, that is less lambda required for the transition. Trimethylamine does not show any transition in aqueous solution because amine gets protonated and n electrons, these are n electrons, these are not available for n to pi star transition, n to sigma star, sorry, transition. The third one is pi to pi star transition. These type of transitions involve the excitation of electrons from pi molecular orbitals into pi star anti-bonding molecular orbitals. These type of transitions are shown by compounds containing multiple bonds, that is double or triple bonds, as you can see in these examples. So, for the isolated unsaturated compound, the absorption takes place outside the ordinary UV region, but the intensity of absorption is very high. This is the lambda max wavelength of this molecule, that is 170 nanometer. But when we increase the conjugation in a molecule, here we are adding a double bond in conjugation to this bond, so the wavelength also increases. We will study this in detail also. The last type of transition is N to pi star transition. These type of transitions involve the excitation of electrons from non-bonding atomic orbitals N into pi star anti-bonding orbitals. This type of transitions are shown by compounds containing double bonds between heteroatoms. So in this we also have double bond and we have heteroatoms also. Both of the conditions are required. So this is double bond, heteroatom, and so on. These kind of transition needs minimum energy, and that is also in the range of ordinary spectrometer, but the intensity of absorption is very high. Next comes the transition probability. That is, the probability of a particular electronic transition depends upon epsilon max and some other restrictions called selection rules. Transition by change in spin quantum number do not take place. That is, from singlet to triplet, transitions are forbidden. Transitions with orbitals of different symmetry do not take place at all. That is, n to pi star. The symmetry is changing, so it is also a forbidden transition. Depending upon the epsilon max, transitions have been divided into two categories: allowed transitions and forbidden transitions. If the value of epsilon max is greater than 10 raised to the power 4, these are called allowed transitions. And if the value is less than 10 raised to the power 4, the transitions are forbidden. For example, here we have butadiene. It is in conjugation, therefore the value of lambda is more and epsilon max is also more than 10 raised to the power 4. Here, the value of epsilon is less than 10 raised to the power 4. Therefore, these are forbidden transitions. This transition lie in the same plane and more overlap in excited state. So pi to pi star transitions are highly probable. So example is pi to pi star. For forbidden transitions, these transitions are symmetry forbidden. The probability is very low. The orbitals overlap to a very small extent. Now, what is a chromophore? Any functional group that absorbs electromagnetic radiations, irrespective of the fact that whether it imparts color to the compound or not, is called a chromophore. Earlier, we used to say that anything that imparts color is called a chromophore, but that definition is not true now. We say that whether it imparts color or not, it is a chromophore if it is absorbed in electromagnetic spectrum. So the examples of chromophore are these you can see here. Chromophores are generally divided into two types: pi to pi star and n to pi star. Now, auxochromes. Some groups which do not show any characteristic absorption in the UV region or above 200 nanometer themselves, but when they are attached to a chromophore, they produce a shift in absorption band to the longer wavelength with a simultaneous increase in the intensity of absorption band. These are called auxochromes. They do not show any wavelength of their own, but when they are attached to chromophore, they increase the wavelength. The auxochrome group contain atom with non-bonding electrons like oxygen, chlorine, nitrogen, oxygen, etc. So in this you can tell that this group is a chromophore and the chlorine which is attached is an auxochrome. Due to the attachment of chlorine, the wavelength of this group increases. So due to non-bonding electrons, conjugation increases and lambda max also increases. So here you can see the effect of auxochromes when they are attached to this chromophore. The wavelength of this chromophore is 255 nanometer. When NH2 is attached, it increases to 280 nanometer. When OH is attached, it becomes 270. On attaching chlorine, it becomes 265. And when this group is attached, it becomes 320 nanometer. Change in position and intensity of absorption. The position of lambda max and epsilon max can be modified in different ways by some structural changes or changes in the solvent. Because some groups absorption occurs in far UV region while some cannot be easily studied, these changes can be produced using four kinds of effects. These effects are bathochromic shift, hypsochromic shift, hyperchromic shift, and hyperchromic shift. First is bathochromic shift, and it is also called red shift. The shift of absorption maximum towards the longer wavelength or lower frequency is called bathochromic shift. You can see in this diagram, on x-axis we have lambda max and on y-axis we have epsilon max. On moving from left to right, here we have bathochromic shift, that is from left to right lambda max is increasing and the shift is red shift. And it can be done so by using an auxochrome. When we attach an auxochrome, wavelength increases. By increasing the conjugation, lambda max also increases. Or if we use a solvent of low polarity, lambda max also increases. For example, in acetone in water, the value of lambda max is 264. But if we use a less polar solvent, that is hexane, the lambda max becomes 279. The second is hypsochromic shift or blue shift, that is from right to left to shorter wavelength. This is blue shift or hypsochromic shift. And it can be done by removal of conjugation. The lambda max decreases, that is wavelength decreases. By using a solvent of high polarity, we can decrease the lambda max or wavelength. The third one is hyperchromic effect. This effect involves the increase in the intensity of absorption. This is intensity of absorption on y-axis. It increases as we go up. So, to increase the intensity of absorption, this can be done by the addition of auxochrome. Auxochrome increases the wavelength as well as intensity of absorption. These are some examples. Next, we have hypochromic effect. It involves a decrease in intensity of absorption. That is, we move down in this graph on y-axis. This is hypochromic effect. It is brought about by groups which distort the geometry of the molecule. For example, biphenyls have lambda max of 250 and epsilon max of 19,000. But 2-methyl, if we add 2 methyl groups to biphenyl, the value of lambda max decreases as well as intensity decreases to 10,250. Then comes the most important topic of this chapter, solvent effect. This topic also comes in masters if you want to do masters in chemistry. So try to understand this topic carefully. Solvent effects. The solvent used for dissolving a compound under examination affect the UV spectrum of the compound. The polarity of the solvent may shift the position of absorption towards shorter or longer wavelength depending upon the type of transition. The first type of transition is pi to pi star. So, how a solvent affects or shifts the pi to pi star transition? When we increase the polarity of solvent, the shift of pi to pi star transitions is towards longer wavelength, that is red shift. So, in polar solvents, shift is towards longer wavelength. In ground state, the molecule is non-polar, and in excited state, it is more polar. In this transition, excited state is more polar than the ground state. As a result, hydrogen bonding and dipole-dipole interaction with the solvent molecules lower the energy of excited state and shift the absorption towards higher wavelength. So this is the reason why it is shifted towards higher wavelength. Ethylene molecule is more polar in the excited state. This is an example. So you can see that when we are using a polar solvent, the energy separation is less, and while using non-polar solvent, the energy gap is more. So absorption shift towards longer wavelength. The second is shift in N to pi star transitions. Increase in the polarity of solvent shifts N to pi star transition to shorter wavelength. This is the reverse of this pi to pi star case. So this is a blue shift. More polar, blue shift. In this transition, the excited state is less polar than the ground state. The ground state is more stable than excited state through dipole-dipole interaction and formation of hydrogen bond with the solvent molecule. As a result, the absorption shifts towards shorter wavelength. So you can see here, when a non-polar solvent is used, the energy gap is less, while a polar solvent increases the energy gap. Therefore, for N to pi star transitions, we don't use a polar solvent. Next comes the effect of conjugation. This is also a very important topic. Molecule containing conjugation system shifts absorption towards longer wavelength than in case of non-conjugated system. You can see this is a simple ethene molecule. Its wavelength is 162 nanometer. But when we increase the conjugation, we add double bond in conjugation to this double bond. The wavelength becomes 217 nanometer, which is far more than 162 nanometer. The other example is we have added this conjugated group here and the wavelength increases to 278 nanometer. Due to conjugation, the energy gap between highest occupied molecular orbital and lowest unoccupied molecular orbital is decreased. So, if energy gap is decreased, transition takes place easily. So, lambda max is more. You can see here, this is the diagram of simple ethene molecule. This is psi 1 and this is psi 2. Psi 1 is HOMO and psi 2 is LUMO. And here we have shown a conjugated system. Here HOMO and LUMO energy gap is smaller and energy absorption moves towards higher wavelength. The HOMO and LUMO energy gap is smaller in this case in conjugated system, while the HOMO-LUMO energy gap is more when the conjugation is absent. Therefore, due to lesser energy gap, the transition is much easier and the wavelength is longer. Also, you can see here, more the conjugation, more will be the wavelength. So, this is simple ethene and this is conjugated system. The next topic is Woodward-Fisher rule. So this is also a very important topic of this chapter. We are going to do it in the next video. Okay, thanks for watching. Bye-bye.